and back to what we're doing. Final exams. Woo. All right. Boink, 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 boink. All right. So we're going to do the exam, and if anybody shows up besides the void account, then we will see if we want to do anything else. Otherwise, we will go ahead and stop when we get done to the end. All right. Starting at a tree in a flat pasture, you run 20 meters this way. Oops. Control Z that. Let's get my, let's see, let's write on the right surface. There we go. We go south 20 meters, and then 40 meters in direction of this much, north of east. Okay, go that way. 53.1 degrees, some 40 meters. Where is final distance from the tree? All right. Okay. So we have a x. We're going to break things down into our component directions. Let's see if we can do this right. A, x, and y. Our first one we're going to do south, therefore x is 0 and y is minus 20. And then B, we are going to go to east. We're going to go 40 meters. And then we have 53.1 degrees, which is a 3, 4, 5 triangle. And so using that, we know our x, this is the short one, so this is the 3/5. We go 3 on, 3 over 5, x, and we go back up 40 meters, and this is the long one, 4 on 5. Add those together, and so that ends up being 40 divided by 5 is, that would be 8. Yes. 8 times 3 is 24. And then y here we have 40. 8 times 4 is 32, less 20 is 12. So here's our position in x and y. 24 meters east, 12 meters north. And so then we need to do, let me double check that, make sure I didn't screw that up. 40 times 3/5, 24, and 4/5. 32, less 20, 12. Yep, good. So now we can do our Pythagorean theorem and find out our final distance. So we square that, add them together, take the square root, and the answer is, I'm not going to do that in my head. 24 squared plus 12 squared, square root is 26.8. Alrighty. Now we have a kinematic question. A small rock is projected from the roof of a building with initial speed 20 meters in a direction of 36.9 degrees above the horizontal. Rock strikes the ground 3 seconds after it is thrown. What is the height of the building? Oh boy. Okay. 3 seconds later. Alright, so it goes wee off the top of the building and lands here. H here. We're told time is 3 seconds. 36.9 degrees goes here. H, and then so this is our 0 here. So this is a position question. X is equal to x naught. In our particular case, that means h plus a v naught. So that's 20 meters per second. Oh, and our final destination, this is 0 meters per second. Upwards, we need the this is going to be the short angle here. So that would be the short component's 3/5. T is 3 seconds. Minus 1/2 G 9.8 meters per second squared times the T squared, 3 seconds squared. Seconds cancel seconds squared, seconds cancel seconds, and so this is a meter, that's a meter, this is a meter, which leaves us with an h of meters. Yay, everything makes sense. Evaluate that, so we end up with 0 meters is equal to h plus the rest of that. 20 times 3/5 times 3 is 36. meters. And then when you subtract off, 4.9 times 9, 44.1. And that is equal to 36 minus, clear it, whatever, 44.1, 8 minus 8.1. So we end up with h minus 8.1 meters is equal to 0 meters. Therefore, that 8.1 meters. Block. A 20 kilo block moves on a horizontal frictional surface at force F that has a magnitude of 60 newtons and direction 30 degrees above the horizontal, is applied to the block by a person, and the block slides along the surface. While the block is moving, what is the magnitude of the normal force that the surface exerts on the block? Okay. Okie dokie. So we have do sum of forces in the vertical direction is equal to 0, and we are told that we have a force. We have gravity pulling down. I would like that to be negative, so we're going to have normal pushing up minus gravity pulling down plus the force that is applied in the y direction. There we are. Or that y there. Try not to confuse things. So that means that the normal is equal to force of gravity minus the force applied to it. So that is mg minus F, and then so this here sine, yes, sine 30 degrees, or theta that goes there. So we have 20 kilos, 9.8 meters per second squared, minus 60 newtons, sine 30 degrees. (20 times 9.8 minus 60 times sine of 30. We're in degrees, very good. All right. Nice round number. 166 newtons. Just out of curiosity, was the alternative wrong answer also here? 144? It was not. Yeah, interesting. So if you have messed up and put cosine here, you got 144 and change, and 144 is not provided. How kind. Oh, the 30 Newton here though, that's a trapper though, because it should be a trapper. 60 sine of 30. Yep. This 30 newtons here is this component right here. Oh, and the but 96 is the no, that's not it. 20.98. 196 is though. So 196 is another trap answer here. It's just the this is just our force of gravity. This is our force y. But these other ones are a bit of traps in some way too. 166 plus 60. This is what happens when you put the wrong sign in. You instead of putting minus, you put plus. I don't know what the 96 is about. Anyways. Okay. A block of mass 5 kilos is pulled up a frictionless surface 30 degrees by a constant force F of 70 newtons that's parallel to the surface of the plane. What is the magnitude of acceleration of the block? Alrighty. So, let's draw on the correct surface. There we go. So we have, in addition to frictionless, alright, in addition to the force being applied, we also have force of gravity. So then we need the F gravity parallel. Alright, so then we have force. Sum of forces is equal to, we're going to have force that's applied minus force gravity parallel. We are told that this is, but we need the force gravity parallel, so that turns into F minus mg. Why is my face over there? Give myself a little bit. Mg, and then sine theta. I want sine here because if this was 0, then sine of 0 is 0, and we have no parallel force. So that makes perfectly good sense there. And so then we end up with 70 newtons. Acceleration, all right. 70 newtons minus m, 5 kilos. 9.8 meters per second squared. Sine of 30 degrees. And that answer is 70 minus 5.98. Sine of 30 is 45 and a half. 45 and a half newtons is equal to ma. So then we divide the m over 5 kilograms acceleration. Therefore, my acceleration is somewhere about 9.1 meters per second squared. This 4.9, this is also a bit of a trap. This is for if you, this is just what would happen if you didn't apply F to it. This would be actually 4.9 going down, and this is 9.1 going up. I'll bet this is one of these is what happens when you add them together rather than taking the difference. Yep. 18.9 is what happens if you put plus instead of minus. So this is, yeah, so this would be probably downwards as well. But F would have to be pointing down instead of up. Why is that? There we go. A block with mass m is suspended from the roof of an elevator by a light rope. Okay. When the elevator has downward acceleration of 2 meters per second squared, the tension in the rope is 30 newtons. What is the mass m of the block? Oh, fun. Masses in elevators. That always makes life fun here. All right. Okay, so everything is going down with an acceleration of 2 meters per second squared. Tension is 30 newtons. All right, so on this mass here, we have mg pulling down, we have t pulling up, and overall we're going down with acceleration a. So then that means our sum of forces on this thing, we have tension going up. No, we don't. We're going to go down with positive. So then we have mg going down minus tension going up is equal to ma going down, right? Downward acceleration, yes. So then we'll go ahead and rearrange this for m. G minus a is equal to t. Therefore, m is equal to t on g minus a. Quick idiot check. What happens if the acceleration is equal to 0? Then this becomes, then a goes to 0, and we have t on g, which means the tension in the string is just the amount holding the mass up, and that makes more or less sense. And if a goes to 0, goes to 9.8, then you have division. Then you have a 0 on the bottom, and you go, wait, isn't this a number divided by 0? Isn't that not bad? Well, you also have t, so it would also have to be 0. So you end up with 0 over 0, and then you go, well, you end up with a limit of some sort or other, and we're not going to do that. So that more or less makes some sense there. Basically, you end up with 0 tension over 0, and you end up taking some kind of limit, which would be non-zero, and you end up with, back to non-zero m. You just don't have enough information. You'd have insufficient information as the question was m. If you're in free fall, but you're not, so we're not going to be too terribly concerned about that. All right, plug numbers in. Tension, 30 newtons. 9.8 minus 2 is 7.8 meters per second squared, and the answer is 30 divided by 7.8 is 3.85. 3.85 kilograms. All right. A small block, here we are, has mass of 0.05 kilos, that is indeed a small block. Is released from rest at point A at the top of the large hemispherical bowl with a radius of 0.4 meters. As it slides through point B at the bottom of the bowl, has kinetic energy of 0.2 joules, 0.12 joules. Was work done on the block by friction as the block slides from A to B? All right. Okay. Okay. So we have energy initial is equal to energy final, and then so we start out with mgh is equal to 1/2 mv squared plus the work of friction. H is equal to 1 radius. So, right. And we're all actually told what the kinetic energy is, so we're actually told that this is 0.12 joules here. So then we just plug and play on the right hand side. I don't feel like writing those numbers out. So that's 0.05 times 9.8 times our radius of 0.4. 0.196, like so, joules. So that means that our work of friction is equal to 0.192 minus 0.12 is 0.072 joules. Okay. Oh, interesting. Oh, 6. That's better. Calculator did exactly what I told it to. Good calculator. 0.076 joules goes here. So we strike out that one, now. So now we get to these two here, and we have to make sure we get the right sign. My work of friction is positive because it is on the I put my work of friction on the final side. But if you go back down here to the to the bottom. Come here. That was one too many. Where's my work friction? Here we are. Work other, like a friction, goes on the initial side, not on the final side. Come on. And so I've actually put it on the wrong side. It should be over here on the initial side, which means that this is a minus. Nope. It's right on the correct surface. This is actually a minus here. Which makes more sense when we consider that work is changing kinetic energy, and friction only slows things down. Therefore, change in kinetic energy must be less than 0. So this must be minus 0.076. All right. A block with mass of 5 kilos is placed against a compressed spring with has 40 joules of elastic potential energy stored in it. The spring is released and the block travels a distance of 2 meters along a horizontal surface until it comes to rest. What is going to horizontal surface? Very good. What is kinetic friction? Coefficient of kinetic friction between the block and the surface. Oh boy. Okay. So we have that the work of friction is 40 joules. There is no other way to dissipate this energy. We started out with 40 joules, we turn into kinetic energy, and then that kinetic energy turns into friction. That turns into work done by friction. So that work of friction is equal to 40 joules, which is equal to FD. We're told D. So force of friction is equal to mu force normal. There's no other forces acting on this, so that force normal must be equal to force of gravity. So that's mg. So this is equal to the work over oops, no. Yeah. Work done here, and then so we end up with mu is equal to the work divided by distance times force of gravity. So that's 40. Let's try it again. Come on. Try that 40 again. 40 joules divided by the distance traveled 2 meters times the mass of 10 kilos times gravity 9.8 meters per second squared. Meter times meter is meters squared per second squared times kilograms. Kilogram meters squared per second squared is a joule. Joule divided by joules, those all go away. So this is 10, so we end up with 4 over 9.8. And I don't know what that is. 0.408. Right here. A small rock is thrown straight up from the surface of the planet. The rock has an initial speed of 8 meters and reaches a maximum height of 10 meters above the surface. If the radius of the planet is this much, what is its mass? Alright, this is a two-step question. First question is, what is the acceleration due to gravity on the surface of this planet? Speed of 8 meters goes to 10 meters in height. Okay. V squared is equal to V naught squared plus 2AD. I believe this is what order we're going to go for. Yeah. Doesn't matter. So then we have 8 meters per second quantity squared. Make that equal to 0. And because this is our initial height, our velocity at the top is equal to 0. At the same time that we have 2g 10 meters here. So we end up with 64 meters square per second square divided by 20 meters. Meters cancels a meter here, and we end up with meter per second square, which is an acceleration. And so we end up with 64 over 20, 3.2. Yep. 3.2 meters per second squared. All right, so now we have a gravity, and this is equal to capital G m on r square. We have an r, we have the g, we need the m here. So we end up with little g r squared divided by big G is equal to m. All right, 3.2 times that number there, 3.2 times the radius of 6 times 10 to the 6 divided by 6.67 times 10 minus 11. 6.67 times 10 to the minus 11. All those units should cancel out. If they don't, we have problems. 3.2 times 6 times 3.2 times 6e plus 6 divided by 6 squared there we go, divided by 6.67 e minus 11. 1.72 times 10 to the 24. 73. All right, here we have an inelastic collision. On a horizontal frictional surface block A, mass of 5 kilos, is moving due east with speed of VAI, and block B is moving with mass of 10 kilos, moving due north with speed of VB. Blocks colliding together. Immediately after collision, these combined object 15 kilos is moving in this direction here. What is the speed of VA of block A before the collision? Okay. We're not told the initial velocity of A. Alright. Okay. Well, we can examine this as one-dimensional question here. We only need to know about our horizontal direction. We don't care about the vertical direction, so we need to actually get the horizontal component out of this. So our V final is equal to 8 meters per second times, mostly aligned with that direction, is 4/5. That is a roundish number, but not that round. 32 over 5 is 6.4. Ha! 6.4. 6.4 meters per second. So now we can do our momentum initial is equal to momentum final. MAV initial is equal to MA plus MB, V final. So V initial is equal to 15 kilos, 6.4 meters per second, divided by 5 kilograms? Yes. So that's a 3 times that number there. Times 3, 19.2. Meters per second. Alright. A small rock with a mass of 1/2 kilo is attached to the lower end of a light string of length 2 meters. If the upper end of the string is attached to the ceiling, the rock is released from rest with the string going horizontal, swings downwards in a circular arc. As the rock swings through its lowest point, what is the tension in the string? Okay. So I'm going to answer some different questions in addition to the question that has been asked. So the first question that we need to answer, need more water. The first question that we absolutely need to answer this question is, what is the angular velocity going through here? What is the omega here at this point? Using energy conservation to do that, we should answer that. So we have, let's see here. I'm going to go about it, well, I'm going to go about it in a funny way. We have energy initial is equal to energy final. So we have that the energy we started with mgh is equal to 1/2 I omega squared. You could do this as 1/2 mv squared, but we'll get to the same place. So then we have that this is 1/2 mr squared omega squared. And this is equal to mgh. And then so the omega is equal to 2gh divided by r squared, square rooted. Buzz. That does not require my attention. Equals to square root 2 times 9.8 times the height. R is 2 meters divided by, oh yes, look at that. And I'm going to travel around in a circle, r squared. So we have an omega of 3.13 rads per second. You would find, therefore, that V, if you'd gone mgh is equal to 1/2 mv squared, you would find that this is equal to, multiply that by 2. Yep. 6.26 meters per second. But there's another omega. Just out of curiosity, what is the angular frequency of this pendulum? Angular frequency of that pendulum is, where is it? Here it is. Right? Oop. That's period. Frequency, there we are. Square root of g on L. Square root of 9.8 divided by 2. 2.21 rad per second. So this is a angular velocity of 3.13 rads per second, and this is an angular frequency of 2.21 rads per second. These are very different things, and they should not be. They should hopefully, with much practice and patience, not be confused. Fortunately, this question was not asking about that. Therefore, we shall not be lingering on it too long. Now we go back to our question was tension. So we have gravity pulling down, mg, and we need a force centripetal going up, F cent, which is equal to mr omega square. So we have tension, we have force centripetal going up, is required for motion, is therefore equal to tension, tension going up, yes, minus gravity coming down. Therefore our tension is equal to mr omega square plus mg. So that's oh, look at that. We have a half kilo here and an r here, which is 2. Therefore these are actually gone, and so we end up with, so that's effectively gone. There's a unit conversion. It turns into a unit conversion here, so this comes out so that we end up with newtons coming out the side here. So that would be a newton second squared. 1 newton second squared, so this comes out correct. So back up here. Okay. So we have square that plus a half kilo times 9.8 is 14.7 newtons. This should be the same as, let's see here. This would be mv square on r plus mg. Just out of curiosity, that would be a half, right? Yep, a half times 6.26 squared divided by 2 plus 0.5 times 9.8. 14.69, 14.7. Ta-da! Very good. Uh, 9.8 is here for you, for people who don't realize that this thing is moving, and therefore we need to have some more tension in it. 4 point, I'm not sure what any of the rest of these are. I suspect one of them is what happens if you take difference instead of the addition. Yep. The 4.9 is for people who decide to take the difference, so take the difference instead of adding them together, which means that I suspect that the 1.5 is going to be just the mv squared here, right? Nope, that doesn't sound right. I don't think that's right. Oh, I'll bet that's 9.8 there. Yeah. But yeah, I'll bet these numbers have been picked in such a way that if you look at this, the 2, h, and r all cancel out, and you basically end up with the square root of g with the correct units. Square root of 9.8. Yeah. So this is either for people who just take gravity, or people who just go for the centripetal the centripetal force, and I don't know what the 1.5 is about. But yeah, I don't know what the 1.5 is about. Anyhow, moving on. A uniform bar with length of 1.2 meters and mass of 3 kilos is attached to a lower end of a wall by frictionless hinge. The bar is held in place by an angle 53 0.1 degrees of the horizontal by a horizontal rope that is connected between the upper end of the bar and the wall. There is tension in the horizontal rope. Okay. So this is a sum of torques is equal to 0. So pulling down, let me guess, everyone is still no one. We have mg pulling down, so we have torque due to gravity minus the torque due to tension. So we have mg L at half the length, sine of this angle here, so that's 90 minus the theta. Solving this, we can set those equal to each other. It's equal to t at the full length sine at this angle here, which is the same as this one provided to us. L's cancel each other, and so then we end up with mg. Move the 2 to the other side. Do we want to do that? No, we don't. We're going to leave t here. We're going to leave the 2 here. Sine becomes cosine divided by sine theta. So this is our tension, and this is also equal to 2 tangent theta under mg. Punching that into our trusty calculator. M is 3. Don't care what the length of that or the stick is. The length has been provided for your convenience to have a number. Because, yeah. Well, moving on. 9.8 divided by 2 tangent angle provided is 53.1. Execute. 11.1 newtons. 11.0 newtons. I'll bet one of those is what happens when you put tangent on top. Times tangent of 53.1 divided by 2. 19.6, yep. And this one here is provided for people who get their angles backwards. So if you get your angles backwards, then you basically end up with sine theta over cosine theta, which is tangent theta instead of cotangent theta. A uniform disk with a certain radius and mass is rotating about a fixed axis at its center. Moment of inertia of the disk is going to be 1/2 mr squared, just as I said. If the kinetic energy of the disk is 4 joules, what is the magnitude of the linear velocity of a point on the rim of the disk? Alright, so we have that kinetic energy is equal to 1/2 I omega squared is equal to 1/2 another half mr square, and then we want to change out the omega for a velocity because we want linear velocity, so then we end up with v on r square. R's cancel, and so we end up with our kinetic energy is equal to 1/4 mv square. So we end up with 4 kinetic energy, 4 joules, divided by a mass of 2 kilograms square rooted is equal to something. Is equal to v. So 16 divided by 2 is 8. So this is exactly equal to square root of 8 meters per second. That's going to be more than 2 and less than 3. square root of 8, more than 2 and less than 3. – 2.83 meters per second. All right. Next question. Let's see the questions. All right, 2 more pages. A block is attached to a horizontal spring and moves in simple harmonic motion as on a frictionless surface. The amplitude of the motion is 1/4 meter. The period of the motion is 3 seconds. What is the period when the amplitude is increased to 1/2 meter for the same block and spring? All right. Well, turn that off. We have a period given to us. Here we are, period. 2 pi times mk. Period is equal to 2 pi square root of m on k. All right. What's the period when the amplitude is changed? Amplitude has no input in here. Try that again, eh? No way. Therefore, it does not care if the amplitude has been doubled. Therefore, the period is still 3 seconds. A block with a mass of 3 kilos attached to a horizontal spring with a force constant of 300 newtons per meter. All right, we got an M, we got a K. And moves in simple harmonic motion on a horizontal frictionless surface. At one point in the motion, the block is 0.4 meters to the left of equilibrium position and is moving to the left with a speed of 6 meters per second. What is the amplitude of motion? Alrighty. So we have energy initial is equal to energy final. Energy initial given to us is 1/2 mv squared plus 1/2 kx squared. And then our energy final is a maximum amplitude of 1/2 kxka square. All right, all the halves cancel out. We could divide k to the other side, but I think I'll just go ahead and plug and play. So we have a mass of 3 with a velocity of 6 plus k of 300 and a position of 0.4 squared is equal to, well, we'll go ahead and just punch in all the things in. K is again 300. And then we take the square root of that whole mess, and that is our A. Square root began 3 times 6 squared plus 300 times 0.4 squared, and yep, got the beginning, divide by 300. 0.72. meters. This 0.4 is here for people who just go, oh yeah, here's a 0.4. That must be our amplitude there. The rest of them don't know. But of course, the amplitude must be greater because we still have kinetic energy here. If kinetic energy was 0, then indeed that'd be 0.4, but it's not. All right. Interfering sound waves. Lovely. Speakers A and B emit waves in phase and with wavelength lambda. Speaker B is 6 meters to the right of speaker A, and point P is 3 meters to the right of speaker B. What is the largest value of lambda for which there will be a constructive interference at point P? Okay. So that means all right. So we need a sound wave to arrive in phase with point B. So that point B can add its value to this bit here. So we only care about the 6 meters here. I'll bet I can draw a wave. All right, here's a wave that will fit in this interval and arrive. Oh, this would be out of phase. No, we don't want that. We want it to arrive in phase. We want to arrive in phase. There we go. This will arrive in phase. The other one will arrive out of phase and then it'll cancel. And we don't want that. So this one will arrive in phase. So that means that 6 meters is our lambda. We'll think about that. There's a 2 kilogram, calorimetry. Let's see if we can get it right the first time on this one. All right. There's a 2 kilogram block of ice that is 0 degrees Celsius in an insulated container of negligible mass. A piece of metal with mass of 0.8 kilograms and temperature of 350 degrees Celsius is placed in the ice. After thermal equilibrium has been reached, the final temperature of the system is 50 degrees Celsius. What is the specific heat capacity of the metal? No, for ice, blah, da, da, and for liquid water, blah, da, da. And, okay, we have our numbers. Oh, lovely. Okay. Okay. Okay, we have all the numbers we need. Let's see if we can get it right the first time. So we have a mass of ice that we need to melt. They need freezing. So we have a mass of ice that we need to melt. Then we need to raise its temperature. A certain amount. And then we need to also drop the temperature of some metal. I'll just call that M. The C for it, and it's delta T. Ice M. And this all needs to be 0. Alright. So then, so we have mass of the ice of 0.2 kilos. We need to melt it. That's 3.34 times 10 to the 5 joules per kilogram. That cancels out. Plus mass of the ice, 0.2 kilograms. We need a specific heat. Now that it is now water, 4190 joules per kilogram Kelvin. We need to raise its temperature 50 Celsius or 50 Kelvin. Plus mass of the metal 0.8 kilos. It's unknown C, and we need to drop its temperature 300 Kelvin, right? Yes. And of course equal to 0. So then, yes, all signs work out good. On the left-hand side, we end up with 0.2 times 3.34 E5. No, 0.2 times 3.34 E5. There we go. Plus 0.2 times 4190 times 50 is a really big number. I'd rather you had not put it in that manner. There it is. That's still not many I really like. Anyways, kilograms, Kelvin, leaves me with 108700 joules. And that has to be equal to, move this to the other side, 0.8 times 300. 0.8 times 300. C to be determined, 240 kilograms per kilogram Kelvin. Move that to the other side, and we find that C is equal to 108700 divided by 240. 452.9 joules per kilogram Kelvin. 453 joules per kilogram per degree centigrade. That works. That is exactly what we're looking for. Email. I might need to know what that's about. Nope, I don't. All right. Okay. Alrighty. A quantity of monatomic ideal gas undergoes adiabatic expansion, in which the volume of gas increases. And in this process, what happens to the temperature of the gas? Alright. Well, let's see here. These are not on your exam. But we're going to do it anyways. We're going to do these anyways because I think it'd be good to have. Because we're completionists around here. So a quantity of monatomic gas, ideal gas, undergoes adiabatic expansion, in which the volume of gas increases. In this process, the temperature of the gas does what? Well, in this particular case, you could do this for yourself by experimentation, or you can find it on the internet. Basically, people vent stuff into the atmosphere, and you can watch it cool off as they do this. You can do it with, say, you could, if you had purpose for doing so, take your spray, spray paint and paint your mural, and while you're doing it, you feel the cannon get cold in your hand, and the nozzle will get cold, and you might get frostbite when you do that. You probably also feel the same thing when you do with hairspray. Propane tanks. So if you go out and do cooking if you go out and cook on a camp stove with a propane tank, your little bottle could frost up. Same thing, adiabatic expansion. So we are decreasing here. In each cycle, a heat engine rejects heat energy of magnitude 300 joules into the low temperature reservoir and does 500 joules of work. In each cycle, how much heat energy does the engine take from the hot side of the reservoir? All right, so we have on the hot side, we have the engine, we have the cold side, and it does work. So energy comes in, some energy goes out as work, some energy goes into the cold. So it gets so we end up with 300 joules getting wasted. We have 500 joules doing work. So we need to know how much of this is happening, how much energy is being pulled out, and that'll be 800 joules. A block with density of 3 megagrams per cubic meter. Megagram, also known as metric ton, per cubic meter, and mass of 6 kilograms, is suspended from the end of a string while totally immersed in a liquid of density 2 megagrams, 2 metric tons per cubic meter. What is the tension in the string? All right. So we need from this So what's going on here is buoyancy. And so the force that's being, our force of buoyancy, try that again, buoyancy is equal to the force of gravity of displaced stuff. So we need to find that force of buoyancy first. And in order to do that, we need to find the volume. We need to have the mass of the stuff displaced. And to do that, we need the volume of the stuff displaced. So that's what these two things are here for. So we need to know, volume being equal to mass divided by density. So we have 6 kilograms divided by 3,000 kilograms per cubic meter. Kilograms cancel each other. Inverse cubic meter on the bottom comes to the cubic meter on top, which means that our units work out correctly. 6 divided by 3,000 is 0.002 cubic meters. 0.002 cubic meters. Now we can find the mass of the stuff displaced. So that's mass. Oops, no, it's not. That is a density times volume. So that is it's not. It's 2,000 kilograms per cubic meter times 0.002 cubic meters. And so times 2,000 is 4 kilograms. Okay, so now we can come back over here and find our tension. Tension pulling up, buoyancy pulling up, and gravity pulling down, all equals 0. So we have that, we have mg is equal to m displaced g plus tension. So we end up with mass of 6 minus 4, 9.8, and that is tension. So 19.6. A U-shaped tube open to air on both ends contains some mercury, density given, a quantity of water, density given, is poured slowly into the left arm of the tube until a vertical height of the column of water is 60 centimeters. What is the vertical height? What is the vertical distance between the surfaces of the mercury and the two arms of the tube? Okay. Right. So the mass of this water is equal to the mass of this mercury over here. So then we have, so we have a volume is equal to area height. So we have area height, density of water. Let's try this again. Area height, density of water is equal to area height, density of mercury. Areas cancel each other. This H is given, the rows are given, so the H we are interested in is this one here, so that is 60 centimeters. density of water, 1,000. Back it up. Is 1,000. Units are the same, so the units of densities are the same, so kilograms per meter squared, cancel kilograms per meter squared. 13.6 times 10 to the 3. And that is equal to 60 times 1 divided by 13.6, 4.41. And that should be the end of the exam. Yes. So those last few questions were basically looking at the density. We're looking at density stuff here. I think that's mostly it. Really? It's just density? I thought there was some, well, I guess there's some ideas that you had to have hanging around. So you had some density stuff there. You had some engine stuff going on, which would have been this stuff up here, but didn't really need much of this stuff. Most of it was, yeah. We didn't really touch that stuff a whole lot about what you really needed or didn't need. So I'll just go ahead and talk about these equations here at the end real quick. So we have the let's see here. Let me click on the right side just in case. Come here. There we are. Just in case I want to write on it. So this first equation is the heat heat coming in or out of a gas. It's kind of like this one here, except it's for if you're trying to compress it or make it bigger, right? All right. If you're trying to use so it's the heat coming in or out of a gas when you change its volume or when you change its pressure. If you were to do it with the temperature at constant, then this would be equal to 0. And if you were to do it adiabatically, then it should also be 0. Yeah, because it's too fast for the heat to move. But that's adiabatic. But if the change in temperature is 0, then that is. This is work for if the pressure is constant. Work done by a gas if its pressure is constant, but its volume is obviously not. This is work done for the temperature being constant, and this is the change of internal energy given of the gas given the heat flow in or out of it and the work that it did. This is the specific heat of air of the gas for when you do it. And how they relate to each other. CV is for constant volume and CP is meant for constant pressure. They're not equal to each other, surprisingly enough. These two are for when adiabatic expansion compression happens. Pressure 1, pressure 2, volume 1 and 2. Gamma is the ratio of CP and CV. And then these are works. This is the work done by. Let's see here. Yeah, this is work done of an engine, given the heat from the hot side and the cold side. This is the efficiency of an engine when you have some amount of work done and the heat coming out of the hot side. This is what they call the coefficient of refrigeration, I think it is. I forget exactly what it's called. But it's basically the amount of cold done given the work that you put into the refrigerator. basically the engine, how well the engine works backwards. This is the I don't know why you bother using this for Carnot engine. Carnot engines are the most efficient engines possible, theoretically possible. Hurricanes make decent approximations of Carnot engines. And then this is the efficiency of a Carnot engine, given this particular fact here. And then delta S is entropy coming in or out of out of a region. So if you were melting ice, then you could use this Q here, the Q from latent heat of fusion, to melt the ice, and then you could find the entropy for melting ice from that. Or you could look at this particular thing up here, and then you could say, oh yes, if Q is equal, if we're doing this isothermically, doing an isothermal expansion and compression, then the Q is equal to 0, and therefore, right, Q, yeah. Yeah. Is that really how that works? Q. Something smells a little funny around here, because you should be able to do some. Oh yeah. No, that's how Carnot engines are most efficient. So during their isothermal cycles, you use this Q here, being delta T is equal to 0. Therefore, you have no change of entropy. And then during the adiabatic cycles, Q is equal to 0 because they're moving too fast, or whatever it is, because it's an adiabat, and so you get Q equals 0 again, and then you get no entropy out of the engine. I think that's how that works. Which means that because there's no change of entropy, the Carnot engines are the most efficient. I think that's about it. And I think that's more or less the rest of it. So this is like what is this? Oh, this is the I think this is the buoyancy here. I think this is the no, it's not quite buoyancy. It's related to buoyancy. Between these two here, you get buoyancy out of it. I thought there was something involving airplane wings around here, whatever that is. Anyways, I don't see it. It must be in one of the other chapters that we didn't go through. 13, 14, 13. I don't remember. Anyways, well, that's all of that. I don't think I have collected any. No one in my Zoom to ask if there are questions. Chat looks pretty dead. Oh, look at that. There are some people in chat. Sungun. Does chat have any questions? Because chat's been pretty dead. Yeah, about. During the break, I saw their latency was about 10 seconds, so you got about 10 seconds. 10. Well, given no questions from chat, I'll go ahead and stop here and upload my videos, and then we'll see what goes on from there next week.